Welcome back to Science with Sleepy, where curiosity meets calm, and tonight's journey takes us across centuries to imagine a meeting between one of history's greatest minds and one of today's most powerful technologies. Maybe you had a long day, or maybe your mind is full of questions about how the world works. Either way, tonight you do not have to do anything at all. You can just lie back, breathe slowly, and let your imagination drift through time and science. If you find that these long, gentle stories help you rest, you might like having them waiting for you whenever you need them. When you subscribe, each new journey through science will be there, ready to keep you company at the end of the day. It also quietly helps others who like sleepy science find their way here, one curious mind at a time. Tonight we explore a fascinating question. What if Isaac Newton had access to quantum computing? Travel back to England in the 1600s, when Newton was discovering gravity, inventing calculus, and unlocking the secrets of light. Imagine him encountering a quantum computer, a machine that works in ways he could never have dreamed of. Through this journey we learn what quantum computing actually is, how it works, and why it matters. Quantum computing might have transformed Newton's work on gravity and planetary motion. It could have revealed the quantum nature of light centuries before scientists understood it. This powerful tool relates to mathematics, physics, and the fundamental nature of reality. By the end of this calm journey, you will understand quantum computing in simple terms. You will see how it connects to Newton's discoveries. And you will have drifted through a peaceful exploration of one of science's most fascinating technologies. You do not have to remember every detail. You can let the ideas wash over you like gentle waves. If you drift off in the middle, that is perfectly fine. The story will keep going without you, like a quiet river that flows, even when your eyes close. Picture England in the year 1665. The air smells of wood smoke and damp earth. Horses clop along cobblestone streets. In the distance, church bells ring. This is Isaac Newton's world. Newton was born in 1643, in a small village called Woolsthorpe. His father died before he was born. His mother remarried when he was 3, leaving him with his grandmother. As a child, he was quiet and curious. He liked to build things: windmills, water clocks, kites with lanterns attached. He watched how things moved, how light fell, how objects behaved. Historians who study Newton's life know that he was not always the confident genius we imagine today. He was often unsure of himself. He kept his discoveries secret for years, afraid others might criticize them. He worked alone, in quiet rooms, with only paper, ink, and his own thoughts. In 1665, when Newton was 22, a terrible disease called the plague swept through England. The university where he studied closed its doors. Newton returned to his family home in the countryside. There, with nothing but time and his own curiosity, he began some of the most important work in the history of science. During this year, which historians now call his Annus Mirabilis, or Wonderful Year, Newton made discoveries that would change everything. He thought about gravity. Why do apples fall from trees? Why does the moon stay in orbit around Earth? He realized that the same force that pulls an apple down also keeps the moon circling our planet. This was a revolutionary idea. Before Newton, people thought that earthly things and heavenly things worked by different rules. Newton showed they were connected. He invented calculus, a new kind of mathematics. Calculus lets you calculate things that change continuously, like the speed of a falling object, or the curve of a planet's orbit. Newton needed this math to describe gravity. Without it, he could not have shown how his laws of motion worked. He studied light. He darkened a room and let sunlight stream through a small hole. He placed a glass prism in the path of the light. The white light split into colors: red, orange, yellow, green, blue, indigo, violet. Newton realized that white light is not pure. It is made of all colors mixed together. He developed 3 laws of motion. The first law says that objects at rest stay at rest, and objects in motion stay in motion, unless something pushes them. The second law says that force equals mass times acceleration. The third law says that for every action, there is an equal and opposite reaction. These discoveries did not come quickly. Newton worked slowly, carefully, testing each idea. He did calculations by hand, filling page after page with numbers and equations. He performed experiments, watching how things behaved, measuring what he could measure. The tools he had were simple: paper and ink, simple measuring devices, his own eyes and hands, his mind which could see patterns others missed. Imagine Newton sitting at a wooden desk, a candle flickering beside him. He dips his quill in ink and writes equations. He calculates the motion of planets, working through long chains of mathematics. Each calculation takes hours. Each mistake means starting over. There are no computers to check his work, no calculators to speed things up, just his mind, his hands, and his patience. This is how science worked for centuries. Careful observation, slow calculation, patient testing. Newton's discoveries were brilliant, not because he had powerful tools, but because he could see connections others could not see. But what if he had had a different kind of tool? What if, sitting on that desk beside his candle and ink, there had been something that could do calculations instantly? Something that could simulate entire systems. Something that worked not with simple on and off switches, but with the strange rules of quantum mechanics. To understand quantum computing, we first need to understand how regular computers work. A regular computer uses bits. A bit is like a tiny light switch. It can be either on or off, 1 or 0, yes or no. There is no in between. When you type on a keyboard, send a message or watch a video, your computer is processing millions of these simple on-off switches, flipping them incredibly fast. Think of it like a long row of light switches. Each switch can be on or off. The computer reads the pattern of on and off switches, does something with that information, and creates a new pattern. This happens billions of times per second. But each switch is still just on or off. Simple, clear, either one thing or the other. A quantum computer works differently. Instead of bits, it uses quantum bits, or qubits for short. A qubit is like a spinning coin. When a coin is spinning, it is not quite heads and not quite tails. It is both, and neither at the same time. Only when the coin stops spinning do you see whether it landed on heads or tails. Until then, it exists in a state of possibility. This strange property is called superposition. A qubit can be in multiple states at once. It can be both 1 and 0 simultaneously. It can be both on and off. This sounds impossible, but it is how quantum particles actually behave. Scientists have known about this behavior for over 100 years. They discovered that tiny particles, like electrons and photons, do not follow the same rules as larger objects. At the quantum level, things can be in multiple places at once. They can exist in multiple states simultaneously. They can do things that seem to break the rules of everyday reality. Quantum computing uses this strange behavior to solve problems in new ways. Imagine you need to find a specific book in a huge library. A regular computer would check each shelf one at a time. It might take a very long time. A quantum computer could check many shelves at once, because it can exist in multiple states simultaneously. It can explore many possibilities at the same time. This does not mean quantum computers are faster at everything. They are not better for watching videos or writing documents. But for certain types of problems, especially problems involving many possibilities or complex simulations, quantum computers can be exponentially faster. There is another strange property called entanglement. When two quantum particles become entangled, they are connected in a way that defies normal understanding. If you measure one particle, you instantly know something about the other, no matter how far apart they are. Einstein called this spooky action at a distance. It seems impossible, but it is real. Scientists have demonstrated entanglement over incredible distances. In 2017, Chinese researchers sent entangled photons from a satellite to ground stations over 1,000 kilometers apart. They showed that the particles remained entangled even at these vast distances, instantly affecting each other despite being separated by hundreds of miles. This experiment proved that entanglement works not just in laboratories, but across the planet. Quantum computers use entanglement to link qubits together. This allows them to process information in ways that regular computers cannot. When qubits are entangled, they can share information instantly, allowing quantum computers to explore many solutions simultaneously. This is what gives quantum computers their power. Without entanglement, quantum computers would be little more than expensive classical computers. Researchers are also exploring quantum entanglement for communication. They are building quantum networks that use entangled particles to send information securely. These networks could create unbreakable encryption, as any attempt to intercept the information would disturb the quantum state, alerting the sender and receiver. China has already built a quantum communication network connecting cities over 2,000 kilometers apart. This network uses quantum key distribution to create secure communication channels that are impossible to hack using classical methods. Today, scientists are building quantum computers. Companies like IBM, Google, and others have created machines with dozens or even hundreds of qubits. These machines are still experimental. They are delicate. They need to be kept extremely cold, near absolute zero. They are sensitive to the slightest disturbance. But they work. They can solve problems that would take regular computers thousands of years. In 2019, Google announced what they called quantum supremacy. Their quantum processor, named Sycamore, solved a specific problem in just over 3 minutes. A problem that would have taken the world's most powerful supercomputer 10,000 years to solve. This was a milestone. It showed that quantum computers could do something classical computers could not, even if the problem was artificial and designed specifically for quantum computers. Google's quantum computing team, Google AI Quantum, has been working on quantum computers for over a decade. They have built multiple generations of quantum processors, each improving on the last. Their research focuses on improving qubit quality, developing better error correction methods, and creating useful quantum algorithms. Google has published hundreds of research papers on quantum computing, sharing their findings with the scientific community. The company has formed partnerships with academic institutions, including NASA, to explore quantum computing applications. They are working on quantum machine learning, quantum simulation, and quantum optimization problems. Google has made some of their quantum computing tools available to researchers, though their quantum computers are not as widely accessible as IBM's cloud-based systems. Google has also invested in quantum software development, creating tools like Cirq, an open-source framework for quantum computing. They are developing quantum algorithms for machine learning, hoping that quantum computers could improve AI systems. The company sees quantum computing as crucial for future technology, investing billions in research and development. IBM has been building quantum computers for years. Their quantum processors have grown from a few qubits to over 1,000. They have created what they call quantum volume, a measure that combines the number of qubits with their quality and connectivity. Each new processor improves on the last. They have built quantum computers that researchers around the world can access through the cloud. Anyone with an internet connection can run experiments on these machines. IBM's quantum computing division has grown into a major business, with hundreds of researchers working on quantum hardware, software, and applications. The company has built quantum computers in multiple locations around the world, including New York, Tokyo, and Germany. They have created a quantum computing ecosystem, developing programming languages, software tools, and educational resources. IBM's goal is to make quantum computing accessible to everyone, not just specialized researchers. The company has formed partnerships with hundreds of organizations, including universities, startups, and major corporations. They work with pharmaceutical companies on drug discovery, financial institutions on risk analysis, and automotive companies on optimization problems. IBM provides cloud access to their quantum computers, allowing partners to run experiments and develop applications. These partnerships help IBM understand what applications are most valuable and how to improve their quantum computers. IBM has also invested heavily in quantum education, creating online courses, tutorials, and certification programs. They want to train the next generation of quantum programmers, recognizing that quantum computing requires new skills and ways of thinking. The company has created Qiskit, an open-source quantum computing framework that makes it easier to program quantum computers. Thousands of developers worldwide use Qiskit to experiment with quantum computing. Scientists are using quantum computers to study molecules and chemical reactions. In 2020, researchers used a quantum computer to simulate a simple molecule called lithium hydride. They calculated its electronic structure, something that becomes exponentially harder as molecules get larger. Regular computers struggle with molecules larger than a few dozen atoms. Quantum computers could one day simulate complex molecules, helping design new drugs and materials. Pharmaceutical companies are exploring quantum computing for drug discovery. They want to simulate how molecules interact with proteins in our bodies. Understanding these interactions could help design better medicines. It could reduce the time and cost of developing new drugs. Some companies are already running experiments on quantum computers, testing algorithms that might one day revolutionize medicine. Merck, one of the world's largest pharmaceutical companies, has partnered with quantum computing companies to explore drug discovery applications. They are using quantum computers to simulate molecular interactions, hoping to design better cancer treatments and other medicines. The company has invested millions in quantum computing research, recognizing its potential to transform drug development. Roche, another major pharmaceutical company, is collaborating with quantum computing researchers to study protein folding. Understanding how proteins fold into their three-dimensional shapes is crucial for drug design, but it is extremely difficult to simulate. Quantum computers could model these complex processes more accurately than classical computers. Roche is testing quantum algorithms for protein folding, hoping to accelerate drug discovery. Boehringer Ingelheim has launched quantum computing initiatives to study molecular dynamics. They want to understand how drug molecules move and interact with their targets at the quantum level. The company is working with quantum computing startups and academic researchers to develop new methods for molecular simulation. They believe quantum computing could reduce the time needed to develop new drugs from years to months. Pfizer has invested in quantum computing research through partnerships with technology companies. They are exploring how quantum computers could help design vaccines and treatments more efficiently. The company sees quantum computing as a potential game-changer for pharmaceutical research, though they acknowledge that practical applications are still years away. Financial institutions are exploring quantum computing for risk analysis and portfolio optimization. Banks need to understand how markets might behave under different conditions. They need to find the best investment strategies among millions of possibilities. Quantum computers could explore these possibilities faster than classical computers. Some banks are already partnering with quantum computing companies to explore these applications. JP Chase has been one of the most active banks in quantum computing research. They have partnered with IBM, Google, and other quantum computing companies to explore financial applications. The bank has a dedicated quantum computing team that runs experiments on cloud-based quantum computers. They are testing quantum algorithms for portfolio optimization, risk analysis, and fraud detection. JP believes quantum computing could transform financial services, though they acknowledge that practical applications are still developing. Goldman Sachs has invested heavily in quantum computing research. They are exploring how quantum computers could improve trading algorithms and risk management. The investment bank has partnered with quantum computing startups and is testing quantum algorithms for financial modeling. They see quantum computing as potentially revolutionizing how financial markets operate, enabling faster and more accurate analysis of complex market conditions. Barclays has launched quantum computing initiatives focused on fraud detection and cybersecurity. They are exploring how quantum computers could identify fraudulent transactions more quickly and accurately. The bank is also studying quantum encryption methods to protect financial data. Barclays has partnered with quantum computing companies and academic researchers to develop these applications. Wells Fargo has established a quantum computing research program to explore applications in risk management and customer service. They are testing quantum algorithms for credit risk assessment and portfolio optimization. The bank sees quantum computing as a way to improve financial services while reducing costs. They are working with quantum computing companies to develop practical applications. MasterCard has invested in quantum computing research to improve payment processing and fraud detection. They are exploring how quantum computers could analyze transaction patterns more efficiently, identifying fraudulent activity faster than classical computers. The company has partnered with quantum computing startups and is testing quantum algorithms for financial applications. Material scientists are using quantum computers to design new materials. They want to create superconductors that work at room temperature. They want to design batteries that last longer and charge faster. They want to discover materials with specific properties, like being incredibly strong but also lightweight. Quantum computers could simulate how atoms arrange themselves in these materials, helping scientists find the perfect combinations. Superconductors are materials that conduct electricity with no resistance, but they only work at extremely low temperatures. If scientists could create superconductors that work at room temperature, it would revolutionize technology. Power lines could transmit electricity without loss. Maglev trains could levitate more efficiently. Medical devices like MRI machines could be smaller and cheaper. Quantum computers could simulate how different materials might achieve superconductivity at higher temperatures, helping scientists design better superconductors. Battery researchers are using quantum computers to design better battery materials. They want to understand how lithium ions move through battery materials, how different materials affect battery performance, and how to design batteries that store more energy and charge faster. Quantum computers could simulate these processes at the atomic level, revealing insights that classical computers cannot provide. Some researchers are already using quantum computers to study battery materials, though these applications are still in early stages. Researchers are exploring quantum computing for designing new catalysts, materials that speed up chemical reactions. Catalysts are crucial for many industrial processes, from manufacturing chemicals to cleaning exhaust gases. Better catalysts could make these processes more efficient and environmentally friendly. Quantum computers could simulate how different materials catalyze reactions, helping scientists design better catalysts. Some companies are already exploring this application, testing quantum algorithms for catalyst design. Scientists are using quantum computers to study materials for quantum computing itself. They want to find better materials for building qubits, materials with longer coherence times and lower error rates. They want to design better quantum error correction codes and quantum algorithms. Quantum computers are being used to improve quantum computers, creating a feedback loop that could accelerate progress in the field. Cryptographers are both excited and worried about quantum computing. Quantum computers could break many of the encryption methods we use today. The RSA encryption that protects online transactions relies on the difficulty of factoring large numbers. Quantum computers could factor these numbers efficiently, breaking the encryption. But quantum computers could also create new, unbreakable encryption methods. Quantum key distribution uses the properties of quantum particles to create codes that cannot be copied or intercepted without detection. Researchers are exploring different ways to build quantum computers. Some use superconducting circuits, tiny loops of wire cooled to near absolute zero. Some use trapped ions, atoms held in place by electric fields and manipulated with lasers. Some use photons, particles of light, to carry quantum information. Each approach has advantages and challenges. Superconducting qubits can be made using existing chip manufacturing techniques. Trapped ions are more stable but slower. Photonic quantum computers could work at room temperature, but are harder to control. Major technology companies are investing billions in quantum computing research. Beyond IBM and Google, companies like Microsoft, Amazon, Intel, and others are developing quantum computing technologies. Each company is taking a different approach, exploring various ways to build and use quantum computers. This diversity of approaches is healthy for the field, as it increases the chances that at least one approach will succeed. Competition between companies is driving innovation, accelerating progress in quantum computing. Startups are also playing a crucial role in quantum computing development. Companies like IonQ, Rigetti, PsiQuantum and others are exploring new approaches and developing innovative technologies. These startups often move faster than large corporations, testing new ideas and taking risks that established companies might avoid. Many startups have been acquired by larger companies or received significant funding from venture capital firms, showing that investors see quantum computing as a promising field. Academic institutions are collaborating closely with companies on quantum computing research. Universities like MIT, Stanford, Caltech, and others have quantum computing research programs that partner with industry. These partnerships help transfer knowledge from academia to industry, accelerating the development of practical quantum computers. Companies benefit from academic expertise, while universities benefit from industry resources and real-world applications. IBM has formed the IBM Q Network, a global community of companies, startups, universities, and research labs working together on quantum computing. Members of this network get access to IBM's quantum computers, software tools, and expertise. They collaborate on developing quantum applications and share their findings with the community. The network includes hundreds of organizations worldwide, from Fortune 500 companies to small startups. This collaborative approach helps accelerate quantum computing development and ensures that practical applications are developed alongside the technology. Google has partnered with NASA and other organizations to explore quantum computing applications. They have created the Quantum AI Lab, a collaboration between Google, NASA, and the university's Space Research Association. This partnership allows researchers to access Google's quantum computers and work on problems relevant to space exploration and scientific research. Google has also formed partnerships with academic institutions worldwide, supporting quantum computing research and education. Microsoft has created the Microsoft Quantum Network, bringing together companies, universities, and research institutions to advance quantum computing. Members get access to Microsoft's quantum development tools, including the Q-Hash programming language and Azure Quantum Cloud Services. The network includes companies from various industries, exploring quantum applications in finance, healthcare, energy, and other sectors. Microsoft provides training and support to help members develop quantum applications. Amazon has launched the Amazon Quantum Solutions Lab, helping companies explore quantum computing applications. The lab provides access to quantum computers from multiple vendors, quantum algorithms, and expert consultation. Companies can work with Amazon's quantum computing experts to identify use cases, develop prototypes, and test quantum algorithms. This service makes it easier for companies to experiment with quantum computing without building their own infrastructure. Many companies are forming consortiums to share quantum computing research and costs. These consortiums allow companies to pool resources, share knowledge, and collaborate on developing quantum applications. Some consortiums focus on specific industries, like finance or pharmaceuticals, while others are more general. This collaborative approach helps accelerate quantum computing development and reduces the cost for individual companies. Venture capital firms are investing heavily in quantum computing startups. Billions of dollars have been invested in quantum computing companies, showing that investors see significant potential in the field. These investments help startups develop their technologies, hire researchers, and build quantum computers. Some quantum computing startups have become unicorns, companies valued at over $1 billion, even before they have practical products. This shows the high expectations for quantum computing's future. IonQ went public in 2021, becoming one of the first quantum computing companies to be publicly traded. The company was valued at over $2 billion, despite not yet having practical quantum computers. This shows that investors are betting on quantum computing's long-term potential, even if near-term applications are limited. Other quantum computing startups are also raising significant funding, with some receiving hundreds of millions of dollars from venture capital firms. Rigetti Computing also went public, raising funds to continue developing their quantum computers. The company has built quantum processors and is developing software tools to make quantum computing more accessible. They are focusing on near-term applications, using quantum computers for specific tasks, while classical computers handle the rest. This hybrid approach might be more practical in the short term, before fully fault-tolerant quantum computers are available. PsiQuantum has raised over $600 million in funding, one of the largest funding rounds for a quantum computing startup. The company is working on building photonic quantum computers, which could work at room temperature. Their goal is ambitious, building a 1 million-qubit quantum computer. While this goal is far in the future, the significant funding shows that investors believe in their approach. Other startups are also raising significant funding. Xanadu is developing photonic quantum computers and has raised tens of millions of dollars. Cold Quanta is working on neutral atom quantum computers. Quantum Machines is developing control systems for quantum computers. The diversity of approaches and significant funding shows that the quantum computing industry is maturing, moving from research to commercialization. Corporate venture capital arms are also investing in quantum computing. Companies like Google Ventures, Intel Capital, and others have invested in quantum computing startups. These investments help established companies stay connected to cutting-edge research and potentially acquire promising technologies. Some startups have been acquired by larger companies, integrating their quantum computing expertise into established organizations. One of the biggest challenges is quantum decoherence. Qubits are fragile. Any interaction with the environment can destroy their quantum state. Heat, vibrations, electromagnetic fields, all can cause errors. Scientists must isolate qubits from everything around them. They cool them to temperatures colder than outer space. They shield them from magnetic fields. They work in carefully controlled environments. Even then, errors occur. Quantum error correction is a field of active research, developing ways to detect and fix errors before they ruin calculations. Despite these challenges, progress continues. Each year brings new records. More qubits, lower error rates, longer coherence times, better algorithms. Scientists are learning how to make quantum computers more reliable, more powerful, more useful. The field is advancing rapidly, driven by curiosity and the promise of solving problems that seem impossible today. Picture Newton's study, late at night. A single candle burns on his desk. Papers covered in equations are scattered around him. He has been working for hours, calculating planetary orbits, trying to understand how gravity shapes the motion of celestial bodies. He leans back, rubbing his tired eyes. The candle flickers, shadows dance on the walls. Then, something strange happens. A soft glow appears in the corner of the room. It grows brighter. A rectangular object materializes, smooth and dark, with a glowing screen. It hovers slightly above the floor, silent and mysterious. Newton stands slowly. He approaches the object cautiously. It does not move, it does not make sound, it simply glows, waiting. He reaches out a hand. The surface is cool and smooth, unlike anything he has ever touched. He runs his fingers along the edge. It feels like polished stone, but lighter, more perfect. The screen lights up, words appear, written in English, though the letters look strange and uniform, as if printed by a machine. Quantum computing system, it says, ready for operation. Newton does not know what these words mean. Quantum, computing, system. These are not words he has heard before, but something in him, some deep curiosity, makes him want to understand. He touches the screen. It responds to his touch, lighting up beneath his finger. A menu appears, showing options he cannot fully comprehend. Simulation, calculation, analysis, modeling. He selects calculation. The screen changes. A simple interface appears, asking him what he would like to calculate. Newton thinks for a moment. He has been working on planetary motion. He has been trying to calculate the exact path of Mars as it orbits the Sun. This calculation has taken him weeks. He has filled pages with numbers, checking and rechecking his work. He types, slowly, carefully, calculates the orbit of Mars around the Sun, accounting for gravitational effects of all planets. The screen processes for a moment. Then, instantly, an answer appears. Not just an answer, but a complete visualization. A three-dimensional model of the solar system appears, showing Mars moving in its orbit. The path is calculated perfectly. All the gravitational interactions are accounted for. The calculation that took Newton weeks is done in seconds. Newton stares, unable to comprehend what he is seeing. How is this possible? How can this device do in moments what took him so long? He touches the screen again. He asks it to calculate something else. He asks it to simulate light passing through a prism, showing how white light splits into colors. The simulation appears instantly, showing photons moving, interacting, splitting into the spectrum he discovered. He asks it to solve a differential equation, the kind of math problem that fills pages of his notebooks. The answer appears immediately, with all the steps shown. The quantum computer shows him something else. It can solve optimization problems that would take classical computers years. In the real world, researchers use quantum computers to optimize supply chains, finding the most efficient routes for delivery trucks. They use them to schedule flights at airports, minimizing delays and maximizing efficiency. They use them to design better traffic systems, reducing congestion in cities. These problems involve millions of variables and countless possibilities. Quantum computers can explore these possibilities simultaneously, finding solutions faster than classical computers ever could. Newton sits back in his chair. His mind races. What is this thing? How does it work? What are its limits? He begins to experiment. He asks it questions. He tries to understand its capabilities. Slowly he realizes that this device does not just calculate faster, it calculates differently. It seems to explore many possibilities at once. It seems to exist in multiple states simultaneously. This is when Newton begins to glimpse something profound. This device does not work like the machines he knows. It does not work like gears and levers. It works like something else entirely. Something that follows rules he has never encountered before. He does not yet understand quantum mechanics. He does not know about superposition or entanglement. But he can see that this device operates according to principles he has never seen. And that realization, that moment of wonder and confusion, begins to change everything. Newton spent years working on gravity. He calculated how objects fall. He figured out how planets move. He showed that the same force that pulls an apple to the ground also keeps the moon in orbit. But these calculations were slow, painfully slow. To calculate a planet's orbit, Newton had to account for many factors: the planet's mass, the sun's mass, the gravitational pull of other planets, the planet's speed and direction. All of these interact in complex ways. The math is difficult. It requires solving many equations simultaneously. Newton did this by hand. He wrote out equations. He solved them step by step. He checked his work. He made mistakes and started over. A single calculation might take days or weeks. Imagine Newton sitting at his desk surrounded by papers. He calculates the position of Jupiter. He accounts for how Saturn's gravity affects Jupiter's orbit. He calculates how Mars affects it. He adds up all these tiny influences. His hand cramps. His eyes grow tired. But he keeps going, because he needs to know if his theory of gravity is correct. The quantum computer simulates the entire solar system. Not just one planet, but all of them. Not just their current positions, but their positions over years, decades, centuries. This happens instantly. Each planet's gravity affects every other planet. These influences change over time. Patterns emerge that Newton could never see with pen and paper. Fascination fills him as he watches. Jupiter and Saturn, the two largest planets, create subtle rhythms in the solar system. Their gravitational dance repeats every few decades, creating patterns that affect all the other planets. Small asteroids are pulled and pushed by planetary gravity. Comets, those mysterious visitors from the outer solar system, are affected by the planets they pass. The quantum computer can simulate not just our solar system, but any solar system. A system with two suns appears on the screen. Planets orbit in figure-8 patterns, complex dances of gravity and motion. What would happen if Earth was slightly closer to the Sun, or slightly farther away? The simulation shows how this would change our orbit, our seasons, our climate. His laws of gravity are tested. What if gravity worked slightly differently? What if it weakened faster with distance? What if it strengthened? The quantum computer simulates each possibility, showing what the solar system would look like. Through these simulations, Newton begins to see something profound. His laws of gravity are correct, but they are not complete. They describe how gravity works on large scales, but they do not explain why gravity exists. They do not explain what gravity actually is. The quantum computer shows him something else too. At very small scales, gravity behaves strangely. When particles are extremely close together, the rules seem to change. Newton's equations still work, but something else is happening, something he cannot quite grasp. This is Newton glimpsing, centuries early, what scientists would later discover: that gravity and quantum mechanics are connected. That at the smallest scales, the rules of physics become strange and wonderful. That his classical physics is part of a larger, more mysterious picture. But Newton does not yet have the language to describe this. He does not have the concepts, he only has the simulations, showing him patterns he cannot fully understand. So he keeps exploring, he keeps asking questions, and the quantum computer keeps showing him possibilities he never imagined. Newton loved studying light. He darkened rooms and let sunlight stream through small holes. He placed glass prisms in the path of the light. He watched white light split into colors: red, orange, yellow, green, blue, indigo, violet. He realized that white light is not pure. It is made of all colors mixed together. When light passes through a prism, each color bends slightly differently. Red bends least. Violet bends most. This separates the colors, creating the rainbow spectrum. Newton believed light was made of particles. He called them corpuscles. He thought light was like tiny bullets, streaming from a source, bouncing off surfaces, entering our eyes. Other scientists disagreed. They thought light was a wave, like ripples on water. Waves can bend around corners. They can interfere with each other, creating patterns of light and dark. Newton argued for particles. He had good reasons. Particles travel in straight lines. They bounce predictably. They explain reflection and refraction. But waves explained other things better, like interference patterns. The debate continued for centuries. Eventually, scientists discovered that light is both. It behaves like a particle sometimes, and like a wave other times. This is called wave-particle duality. It is one of the strangest discoveries in physics. But Newton did not know this. In his time, he could only see what his experiments showed him. He could not see the quantum nature of light. The quantum computer simulates light at its most fundamental level. Photons appear on the screen, the particles of light Newton had imagined. Photons stream from a source. They move in ways that surprise him. But then, something strange happens. The simulation reveals that photons do not always move in straight lines. Sometimes they spread out like waves. Sometimes they behave like particles. They seem to exist in both states at once. Confusion fills Newton's mind. How can something be both a particle and a wave? How can light be both a stream of tiny bullets and a spreading wave? Interference patterns appear on the screen. When two light waves meet, they can cancel each other out, creating darkness, or they can reinforce each other, creating brightness. This happens even when light is sent through one photon at a time. Somehow, each photon interferes with itself, as if it is a wave even when it is alone. These simulations unfold before him. Photons interact with matter in ways he never imagined. They are absorbed and emitted by atoms. Electrons jump between energy levels, releasing photons of specific colors. The spectrum of light appears in a new way. not just as colors separated by a prism, but as photons with different energies. Red photons have less energy, blue photons have more energy. The color we see depends on the energy of the photons. Atoms absorb and emit light in precise ways. When an electron in an atom jumps to a higher energy level, it absorbs a photon. When it falls back down, it emits a photon. The energy of the photon matches the energy difference between the levels. This explains why different elements emit different colors of light. Each element has its own pattern of energy levels. When heated, electrons jump between these levels, emitting photons of specific colors. This is why sodium streetlights are yellow, why neon signs are red, why each element has its own spectral fingerprint. Newton realizes that his particle theory was partly right. Light is made of particles, photons. But these particles behave in ways he never imagined. They exist in superpositions. They interfere with themselves. They are connected through entanglement. He also realizes that his wave theory opponents were partly right too. Light does behave like a wave. But it is not a wave in the way they imagined. It is a probability wave, showing where photons are likely to be found. The quantum computer shows him something else, that matter itself has wave properties. Electrons, the tiny particles that orbit atomic nuclei, also behave like waves. They exist in probability clouds around the nucleus, not in fixed orbits like planets around the Sun. This is Newton, glimpsing quantum mechanics centuries early. He is seeing the strange, wonderful world where particles and waves are not separate things, but different aspects of the same reality. He does not yet have all the pieces. He does not understand why this happens. But he can see it, in the simulations, in the patterns, in the behavior of light and matter, at the smallest scales. Today, researchers use quantum computers to simulate these quantum properties directly. They simulate how electrons behave in molecules, how they form chemical bonds, how they absorb and emit light. In 2021, researchers at Google used a quantum computer to simulate a chemical reaction more accurately than classical computers could. They simulated how nitrogen atoms bond together, a process important for understanding how plants convert nitrogen from the air into usable forms. This kind of simulation could help design better fertilizers, reducing the environmental impact of agriculture. Quantum computers are also being used to study photosynthesis, the process by which plants convert sunlight into energy. Researchers want to understand how plants capture light so efficiently, hoping to design better solar panels. They simulate how photons excite electrons in chlorophyll molecules, how energy moves through the plant's energy system. These simulations require tracking quantum states that classical computers cannot handle efficiently. Researchers have discovered that quantum effects might play a crucial role in photosynthesis. When photons hit chlorophyll molecules, they excite electrons, creating quantum superpositions. These superpositions allow energy to explore multiple pathways simultaneously, finding the most efficient route to the reaction center. This quantum coherence might explain why photosynthesis is so efficient, converting nearly 100% of absorbed photons into usable energy. Classical computers struggle to simulate these quantum effects, but quantum computers can model them naturally. Scientists are using quantum computers to study other biological processes that might depend on quantum mechanics. Some researchers believe that quantum tunneling might help enzymes catalyze chemical reactions more efficiently. Quantum effects might play a role in how proteins fold into their three-dimensional shapes. Quantum coherence might be involved in how birds navigate using Earth's magnetic field. These are still active areas of research, and quantum computers could help test these theories. Quantum computers are also being used to study the origin of life. Researchers want to understand how the first self-replicating molecules might have formed. They simulate how simple molecules could have combined to form more complex structures, potentially leading to life. These simulations require modeling quantum interactions between molecules, something that becomes exponentially difficult as systems get larger. Quantum computers could handle these simulations more efficiently, helping scientists understand how life might have begun. And this glimpse, this early understanding, would change everything. Newton invented calculus. He needed it to describe motion and change. He needed it to solve problems that regular math could not handle. Calculus lets you calculate things that change continuously: the speed of a falling object, the area under a curve, the rate at which something grows or shrinks. Before calculus, these problems were nearly impossible to solve exactly. Newton developed calculus to solve physics problems. He wanted to describe how objects move, how planets orbit, how forces act. Calculus gave him the tools to do this. But calculus calculations are tedious. They require many steps. They involve complex equations. They take time. Newton spent hours, days, weeks solving calculus problems by hand. He filled notebooks with calculations. He checked his work carefully. One mistake could ruin everything. A differential equation appears, the kind of problem that fills pages of his notebooks. The quantum computer solves it instantly. Not just the answer, but all the steps. It shows how it arrived at the solution. The area under a complex curve is calculated precisely. The method appears on the screen. A function is optimized, finding the maximum or minimum value. The quantum computer explores many possibilities simultaneously, finding the answer quickly. But the quantum computer can do more than just solve problems faster. It can solve problems that are impossible for regular computers. Some problems are so complex that even the fastest regular computers would need thousands of years to solve them. These problems involve many variables, many possibilities, many interactions. Regular computers must check each possibility one at a time. Quantum computers can check many possibilities at once. Newton asks the quantum computer to find patterns in numbers. He gives it a sequence: 2, 3, 5, 7, 11, 13, 17, 19. These are prime numbers, numbers divisible only by 1 and themselves. He asks it to find the next 1,000 prime numbers. A regular computer could do this, but it would take time. It would need to check each number to see if it is prime. The quantum computer does this faster, exploring many possibilities simultaneously. He asks it to factor large numbers, to break a big number into its prime factors. This is a problem that gets exponentially harder as numbers get larger. For very large numbers, regular computers struggle. Quantum computers can factor them more efficiently. In 1994, a mathematician named Peter Shor discovered an algorithm that could factor large numbers on a quantum computer. This algorithm, now called Shor's algorithm, showed that quantum computers could break RSA encryption, the system that protects most online communications. This discovery sparked both excitement and concern. It showed the power of quantum computing, but also revealed a threat to digital security. Today, researchers are working on post-quantum cryptography, new encryption methods that even quantum computers cannot break. Shor's algorithm was a breakthrough because it showed that quantum computers could solve certain problems exponentially faster than classical computers. The algorithm uses quantum superposition and entanglement to explore many possible factors simultaneously, finding the correct answer much faster than classical algorithms. However, Implementing Shor's algorithm requires a quantum computer with thousands of high-quality qubits, which does not yet exist. Researchers estimate that breaking current RSA encryption would require a quantum computer with millions of qubits and extremely low error rates. In 1996, another important quantum algorithm was discovered. Lovegrover developed Grover's algorithm, which can search through an unsorted database quadratically faster than classical computers. While this is not as dramatic as Shor's exponential speedup, it could still be useful for many applications. Grover's algorithm could help search through large datasets, find optimal solutions, and solve certain types of optimization problems more efficiently. Researchers have developed many other quantum algorithms since then. The variational quantum eigensolver, or VQE, is designed to find the ground state energy of molecules, which is crucial for chemistry simulations. The quantum approximate optimization algorithm, or QAOA, is designed for optimization problems. The quantum Fourier transform is a fundamental building block for many quantum algorithms. Each algorithm is designed for specific types of problems, taking advantage of quantum properties to solve them more efficiently. Companies are developing quantum algorithms for specific applications. Pharmaceutical companies are creating algorithms for drug discovery. Financial institutions are developing algorithms for risk analysis. Material scientists are designing algorithms for materials discovery. These specialized algorithms could provide advantages even on near-term quantum computers, before fully fault-tolerant quantum computers are available. Quantum machine learning algorithms are being developed to take advantage of quantum properties for AI applications. Some researchers believe that quantum computers could help train certain types of neural networks more efficiently, or discover patterns that classical computers miss. Quantum machine learning could be especially useful for problems involving quantum data, like simulating quantum systems or analyzing quantum sensors. However, it is not yet clear whether quantum computers will provide advantages for most classical machine learning tasks. Quantum optimization algorithms are being developed for a wide range of applications. These algorithms could help solve complex optimization problems in logistics, finance, energy, and other industries. Companies are testing quantum optimization algorithms on real-world problems, exploring whether they provide advantages over classical optimization methods. Some early results are promising, though practical applications are still limited by current quantum computer capabilities. Quantum chemistry algorithms are being developed to simulate molecules and chemical reactions. These algorithms could help design new drugs, materials, and catalysts. Pharmaceutical companies, chemical companies, and material science companies are all exploring quantum chemistry algorithms. Some researchers believe that quantum chemistry will be one of the first practical applications of quantum computing, as it naturally requires simulating quantum systems. Quantum cryptography algorithms are being developed to create secure communication methods. These algorithms use quantum properties to create encryption that cannot be broken, even by quantum computers. Quantum key distribution is already being used in some applications, and researchers are developing other quantum cryptography methods. As quantum computers become more powerful, quantum cryptography will become increasingly important for protecting sensitive information. Quantum random number generators are already being used in some applications. These devices use quantum properties to generate truly random numbers, which are crucial for cryptography and security. Classical computers can only generate pseudo-random numbers, which are predictable if you know the algorithm. Quantum random number generators use the inherent randomness of quantum mechanics to create numbers that are truly unpredictable. Some companies are already selling quantum random number generators for use in security applications. quantum-secure communication systems are being developed to protect against future quantum computers. These systems use quantum key distribution to create encryption keys that cannot be intercepted without detection. Even if a quantum computer could break the encryption algorithm, the quantum key distribution ensures that any attempt to intercept the key would be detected. This provides security against both classical and quantum attacks. Post-quantum cryptography is being developed to create encryption methods that are secure against quantum computers. The National Institute of Standards and Technology is leading an effort to standardize post-quantum cryptography algorithms. These algorithms are designed to be secure against both classical and quantum computers, ensuring that encrypted data remains protected even after quantum computers become powerful enough to break current encryption methods. Many organizations are already preparing for the transition to post-quantum cryptography, recognizing that it will take years to update all systems. He asks it to solve optimization problems, to find the best solution among millions of possibilities. The quantum computer explores many solutions at once, finding optimal answers quickly. Real-world researchers are already using quantum computers for optimization. Volkswagen used a quantum computer to optimize traffic flow in Beijing, finding routes that reduce travel time by significant amounts. The automotive company has been one of the most active in exploring quantum computing applications. They have partnered with D-Wave and other quantum computing companies to solve optimization problems. Volkswagen is exploring how quantum computers could optimize manufacturing processes, design better batteries for electric vehicles, and improve traffic management systems. The company sees quantum computing as crucial for the future of transportation. Airlines are exploring quantum computing to optimize flight schedules and crew assignments. Companies like Airbus have invested in quantum computing research, exploring applications in route optimization and aircraft design. Airlines need to solve complex optimization problems involving thousands of flights, crew members, and passengers. Quantum computers could find better solutions faster than classical computers, reducing costs and improving efficiency. Some airlines are already running pilot programs, testing quantum algorithms on real-world scheduling problems. Logistics companies want to use quantum computers to plan delivery routes more efficiently. Companies like FedEx and UPS are exploring quantum computing for route optimization. They need to plan routes for thousands of vehicles delivering packages to millions of addresses. Finding optimal routes is extremely difficult, involving countless possibilities. Quantum computers could explore these possibilities simultaneously, finding better routes that save time and fuel. Some logistics companies have partnered with quantum computing startups to develop these applications. Automotive companies beyond Volkswagen are also exploring quantum computing. BMW has launched quantum computing initiatives to optimize supply chains and design better materials. The company is exploring how quantum computers could help design lighter, stronger materials for vehicles, improving fuel efficiency and safety. Toyota has invested in quantum computing research, exploring applications in battery design and autonomous vehicle systems. These companies see quantum computing as potentially transforming the automotive industry. In 2021, researchers at D-Wave Systems used a quantum computer to optimize the routes for garbage trucks in a city. They found routes that reduced travel time by 20%, saving fuel and reducing emissions. This might seem like a simple problem, but it involves millions of possible routes. Finding the best one requires exploring countless combinations, something quantum computers can do efficiently. Shipping companies are exploring quantum computing to optimize their global supply chains. They need to decide which ships should carry which cargo, which ports they should visit, and in what order. These decisions affect costs, delivery times, and environmental impact. Quantum computers could find optimal solutions that save millions of dollars and reduce carbon emissions. Some companies are already running pilot programs, testing quantum algorithms on real-world logistics problems. Energy companies are using quantum computers to optimize power grids. They need to balance supply and demand, route electricity efficiently, and integrate renewable energy sources like solar and wind. These sources are unpredictable, making optimization difficult. Quantum computers could help find optimal strategies for managing these complex systems, reducing waste, and improving reliability. Researchers are developing quantum algorithms specifically for power grid optimization, testing them on simulated networks before applying them to real systems. ExxonMobil has invested in quantum computing research to optimize oil and gas operations. The company is exploring how quantum computers could improve exploration, production, and refining processes. They are testing quantum algorithms for reservoir simulation, pipeline optimization, and supply chain management. ExxonMobil sees quantum computing as potentially reducing costs and improving efficiency in energy production. BP has launched quantum computing initiatives to explore applications in energy trading and risk management. The company is testing quantum algorithms for optimizing energy portfolios and managing price risk. They are also exploring how quantum computers could help design better materials for energy production and storage. BP has partnered with quantum computing companies and academic researchers to develop these applications. Shell has invested in quantum computing research through partnerships with technology companies. They are exploring applications in chemical process optimization and materials design. The company sees quantum computing as potentially transforming how energy companies operate, enabling more efficient and sustainable energy production. Shell is testing quantum algorithms for various optimization problems in the energy sector. Renewable energy companies are also exploring quantum computing. Companies developing solar and wind technologies are using quantum computers to design better materials and optimize energy systems. They want to improve the efficiency of solar panels and wind turbines, making renewable energy more competitive. Quantum computers could help design better materials for energy conversion and storage, accelerating the transition to renewable energy. Through these mathematical explorations, Newton begins to see something profound. Mathematics is not just a tool for describing the world. It is deeply connected to how the world actually works. The quantum computer shows him that quantum mechanics is fundamentally mathematical. The strange behaviors of quantum particles are described by mathematical equations. Superposition is a mathematical concept. Entanglement is a mathematical relationship. He realizes that the mathematics he invented, calculus, is part of a larger mathematical framework, that there are mathematical structures he has never imagined, that mathematics and physics are more deeply connected than he thought. He also sees that some problems are fundamentally hard, that no computer, no matter how powerful, can solve certain problems quickly, that there are limits to what computation can achieve. This is Newton glimpsing computational complexity theory centuries early. He is seeing that some problems are easy, some are hard, and some are impossible, that computation has fundamental limits. But he also sees that quantum computing pushes these limits, that it can solve problems regular computers cannot, that it opens new possibilities for mathematics and science. And this realization, this understanding of computation and mathematics, would shape everything that came after. Newton's 3 laws of motion are among the most important discoveries in science. The first law says that objects at rest stay at rest, and objects in motion stay in motion, unless something pushes them. This is called inertia. An object will keep doing what it is doing, unless a force acts on it. The second law says that force equals mass times acceleration. The more force you apply, the more an object accelerates. The more mass an object has, the more force you need to accelerate it. The third law says that for every action, there is an equal and opposite reaction. When you push on something, it pushes back on you with equal force. These laws describe how objects move in everyday life. They explain why a ball rolls down a hill, why a rocket launches into space, why planets orbit the sun. Newton tested these laws with simple experiments. He rolled balls down ramps. He watched pendulums swing. He observed how objects fall. His laws matched what he saw. But Newton's laws have limits. They work perfectly for objects moving at everyday speeds. They work for objects larger than atoms. But at very high speeds, approaching the speed of light, they break down. At very small scales, the size of atoms, and smaller, they break down. Newton did not know this. In his time, he could only observe objects at everyday scales and speeds. He could not see what happens at extreme scales. Motion at everyday scales appears on the screen: a ball rolling down a hill, a pendulum swinging, a planet orbiting. The quantum computer confirms his laws. They work perfectly. Motion at very high speeds unfolds next. An object moving at 90% of the speed of light. The simulation shows something strange. Time slows down. Lengths contract. Mass increases. Newton's laws no longer match what the simulation shows. Motion at very small scales appears. An electron orbiting an atomic nucleus. The simulation reveals that the electron does not orbit like a planet. It exists in a probability cloud. It can be in multiple places at once. Newton's laws do not apply. What happens when objects are both very small and moving very fast? The simulation shows behaviors that seem impossible. Particles that exist in multiple states. Particles that are connected across vast distances. Particles that tunnel through barriers. These simulations unfold before him. His laws are correct, but incomplete. They describe motion at everyday scales perfectly. But they are part of a larger picture. Two different sets of rules emerge. Classical physics, which describes large objects at everyday speeds, and quantum physics, which describes tiny objects and high speeds. These two sets of rules seem contradictory, but they are both true. Something else appears. These two sets of rules are connected. Classical physics emerges from quantum physics. When you have many quantum particles, their quantum behaviors average out, creating the classical behaviors we see in everyday life. This is Newton glimpsing the relationship between classical and quantum physics centuries early. He is seeing that his laws are not wrong, but they are part of a deeper truth. He also sees that his laws have edge cases, situations where they break down, where other rules apply, where the world behaves in ways he never imagined. Through these simulations, Newton begins to understand the limits of his own discoveries. He sees that science is not about finding absolute truths, but about finding better and better approximations, that each discovery reveals new questions. That understanding is always incomplete. This is a humbling realization. But it is also exciting. It means there is always more to discover. Always new mysteries to explore. Always new questions to ask. And this understanding, this recognition of limits and possibilities, would shape how Newton approached science for the rest of his life. Newton believed that matter was made of tiny particles called atoms. He thought atoms were solid, indivisible spheres. They were the building blocks of everything. He was partly right. Matter is made of atoms. But atoms are not solid spheres. They are mostly empty space, with tiny nuclei at the center, and electrons whirling around them. Newton could not see this. In his time, there were no microscopes powerful enough, no way to observe atoms directly. He could only guess based on how matter behaved. An atom appears on the screen. A tiny nucleus, made of protons and neutrons. Around it, electrons exist in probability clouds. They are not in fixed orbits. They exist in regions where they are likely to be found. Electrons jump between energy levels. When an electron absorbs energy, it jumps to a higher level. When it falls back down, it releases energy as light. Atoms bond together to form molecules. Electrons are shared between atoms. Chemical reactions happen at the quantum level. The periodic table appears in a new way, not just as a list of elements, but as a pattern of electron configurations. Each element has a unique arrangement of electrons. This arrangement determines its properties. Why some elements are metals, why some are gases, why some are reactive and others are stable. Quantum mechanics explains chemistry. The behavior of electrons determines how atoms interact. Molecular bonds form and break. Reactions happen. Complex molecules appear on the screen. DNA, with its double helix structure. Proteins, folding into complex shapes. These shapes are determined by quantum interactions. The way atoms bond, the way electrons are shared, the way molecules interact. Today, researchers are using quantum computers to simulate these molecular structures. In 2020, researchers at Google used a quantum computer to simulate a chemical reaction pathway for the first time. They modeled how nitrogen atoms bond together, a process called nitrogen fixation. This reaction is crucial for life on Earth, as plants need nitrogen to grow. Understanding it better could help design more efficient fertilizers, reducing the environmental impact of agriculture. Classical computers struggle with these simulations because they require tracking quantum states that exist in superposition. Quantum computers can handle these states naturally. Pharmaceutical companies are investing heavily in quantum computing for drug discovery. They want to simulate how drug molecules interact with proteins in our bodies. Understanding these interactions at the quantum level could help design medicines that are more effective and have fewer side effects. Some companies are already running experiments on quantum computers, testing algorithms that might one day revolutionize medicine. They simulate how molecules bind to receptors, how they are metabolized, how they move through the body. These simulations could reduce the time and cost of developing new drugs, bringing life-saving medicines to patients faster. Material scientists are using quantum computers to design new materials with specific properties. They want to create superconductors that work at room temperature, eliminating the need for expensive cooling systems. They want to design batteries that store more energy and charge faster. They want to discover materials that are incredibly strong but also lightweight, perfect for building spacecraft or medical implants. Quantum computers can simulate how atoms arrange themselves in these materials, helping scientists find the perfect combinations. In 2021, researchers used a quantum computer to simulate the electronic structure of a small molecule more accurately than classical computers could. This was a small step, but it showed the potential for larger simulations in the future. Something profound emerges. Life itself depends on quantum mechanics. The processes that keep us alive, that allow us to think and move and exist, happen at the quantum level. Photosynthesis unfolds before him. Plants capture light energy. Electrons are excited by photons. This energy is used to build molecules. Enzymes work in mysterious ways. They catalyze chemical reactions. Quantum tunneling allows reactions to happen that would otherwise be too slow. Our senses depend on quantum mechanics. Light enters our eyes and excites electrons in our retina. Sound waves vibrate tiny hairs in our ears. Molecules bind to receptors in our nose and tongue. Researchers are exploring whether quantum effects play a role in how we smell. Some scientists believe that our sense of smell might depend on quantum vibrations in molecules, not just their shape. This theory, called the vibration theory of olfaction, suggests that we can distinguish between molecules that are identical in shape but have different vibrational frequencies. Quantum computers could help simulate these quantum vibrations, testing whether this theory is correct. Some researchers even believe that quantum mechanics might play a role in how birds navigate. Birds can sense Earth's magnetic field, using it to navigate during migration. Some scientists think this ability might depend on quantum entanglement in special proteins in their eyes. Quantum computers could help simulate these quantum effects, understanding how birds might use quantum mechanics to see magnetic fields. All of this happens at the quantum level. All of it depends on the strange behaviors of quantum particles. Newton realizes that his understanding of matter was incomplete. Atoms are not solid spheres. They are complex quantum systems. Their behavior cannot be understood with classical physics alone. He also realizes that quantum mechanics is not just about tiny particles. It affects everything. The properties of materials, the behavior of chemicals, the processes of life, all of it depends on quantum mechanics. This is Newton glimpsing the quantum nature of reality centuries early. He is seeing that the world is more strange and wonderful than he imagined. That quantum mechanics is not just a curiosity but fundamental to how everything works. He does not yet understand all the implications. He does not know how to reconcile quantum mechanics with his classical physics. But he can see that they are connected. That quantum mechanics underlies classical physics. That the strange quantum world is the foundation of the familiar everyday world. And this realization, this understanding of the quantum nature of matter, would change how he thought about everything. Newton believed that space and time were absolute. Space was like an empty container, the same everywhere. Time flowed at a constant rate, the same for everyone. He thought that if you could measure space and time precisely enough, you would find that they were the same for all observers, that a meter was always a meter, that a second was always a second. This made sense for everyday observations. When you measure distance with a ruler, it seems absolute. When you measure time with a clock, it seems constant. But Newton's absolute space and time were assumptions. He could not prove them, he just assumed they were true. Space and time appear on the screen. The simulation shows how they behave at different scales and speeds. Something strange emerges. At very high speeds, approaching the speed of light, time slows down. A clock moving very fast runs slower than a clock at rest. This is called time dilation. Space also behaves strangely. Objects moving very fast appear shorter in the direction of motion. This is called length contraction. These effects are tiny at everyday speeds. You would never notice them. But they are real, they have been measured, they are part of how the universe actually works. Something else appears. Space and time are not separate, they are connected, forming something called space-time. Gravity is not a force pulling objects together, but a curvature of space-time. Massive objects bend space-time, and other objects follow these curves. This is Newton, glimpsing Einstein's theory of relativity centuries early. Space and time are not absolute but relative. They depend on the observer's motion and position. At very small scales, space and time behave strangely. They are not smooth and continuous but quantized. There might be a smallest unit of space, a smallest unit of time. Quantum mechanics and gravity might be connected. Gravity might emerge from quantum interactions. Spacetime might be made of tiny quantum units. Black holes appear on the screen, objects so massive that they bend spacetime completely, where time stops, where space curves back on itself. The early universe unfolds before him, when everything was compressed into a tiny space. Quantum fluctuations might have created the seeds of galaxies. Quantum mechanics affects the large-scale structure of the universe. Quantum fluctuations in the early universe grew into the galaxies and stars we see today. Researchers are using quantum computers to simulate dark matter, the mysterious substance that makes up most of the universe's mass. Dark matter does not interact with light, making it impossible to observe directly. Scientists can only infer its existence from its gravitational effects. Quantum computers could simulate how dark matter particles might behave, helping physicists understand what dark matter actually is. These simulations could test different theories about dark matter's nature, narrowing down the possibilities. Scientists are also exploring whether quantum computers could help solve the mystery of dark energy, the force causing the universe's expansion to accelerate. Dark energy makes up about 70% of the universe's energy, but scientists do not understand what it is. Quantum computers could simulate different theories about dark energy, testing which ones match observations. Understanding dark energy could reveal fundamental truths about the nature of space, time, and reality itself. Through these simulations, Newton begins to understand that his absolute space and time were approximations. They work perfectly for everyday observations. But they are part of a deeper truth. He realizes that the universe is more strange and wonderful than he imagined. That space and time are not fixed and absolute, but dynamic and relative. That gravity is not just a force but a property of spacetime itself. The quantum computer shows him simulations of gravitational waves, ripples in spacetime caused by massive objects accelerating. These waves were predicted by Einstein's theory of relativity but were not detected until 2015, when the LIGO observatory detected gravitational waves from two black holes merging. The quantum computer simulates how these waves propagate through spacetime, carrying information about their sources. Newton watches as gravitational waves from distant cosmic events ripple through the simulated universe, carrying information across billions of light-years. He sees simulations of neutron stars, incredibly dense objects formed when massive stars collapse. A neutron star is so dense that a teaspoon of its material would weigh billions of tons on Earth. The quantum computer shows how these objects bend spacetime dramatically, creating extreme gravitational fields. Newton watches as matter falls into neutron stars, accelerated to incredible speeds by their gravity, releasing enormous amounts of energy as X-rays and gamma rays. The quantum computer simulates white holes, hypothetical objects that are the opposite of black holes. While black holes pull everything in, white holes would push everything out. They are solutions to Einstein's equations, though no white holes have been observed in nature. The simulation shows how matter and energy would emerge from a white hole, creating a cosmic fountain of particles and radiation. Newton watches these simulations, trying to understand whether such objects could exist, and what they would mean for our understanding of the universe. He sees simulations of wormholes, hypothetical tunnels through spacetime, that could connect distant parts of the universe. These are also solutions to Einstein's equations, though they would require exotic matter with negative energy to remain stable. The quantum computer shows how a wormhole might look, a tunnel through spacetime connecting two distant points. Newton watches as particles travel through the wormhole, appearing instantly at the other end, having bypassed the normal distance between the 2 points. These simulations help him understand the strange geometry of spacetime, how it can be curved and folded in ways that seem impossible. He also sees that quantum mechanics and gravity are connected. that understanding one might help understand the other, that there might be a theory that unifies them. This is Newton glimpsing the search for a theory of quantum gravity centuries early. He is seeing that physics is not complete, that there are still mysteries to solve. That understanding space-time and gravity requires understanding quantum mechanics. The quantum computer shows him simulations of loop quantum gravity, one approach to unifying quantum mechanics and gravity. This theory proposes that space itself is quantized, made of tiny loops. At the smallest scales, space would not be smooth and continuous, but made of discrete units. The quantum computer simulates how these loops might interact, creating the fabric of space-time. Newton watches as the simulation zooms in on space itself, revealing a structure made of interconnected loops, like a cosmic network. He sees simulations of string theory, another approach to quantum gravity. This theory proposes that fundamental particles are not points but tiny vibrating strings. Different vibrations of these strings would create different particles. The quantum computer simulates how these strings might vibrate in extra dimensions, dimensions beyond the three spatial dimensions, and one-time dimension we experience. Newton watches as the simulation shows particles as vibrating strings, their vibrations creating the properties we observe. The extra dimensions curl up into tiny spaces, too small to detect directly, but affecting how the strings vibrate. The quantum computer simulates how quantum mechanics and gravity might interact at the smallest scales. At the Planck scale, the smallest possible scale in physics, quantum fluctuations in space-time itself become significant. The simulation shows space-time bubbling and foaming, with tiny black holes constantly forming and evaporating. This quantum foam would be the fundamental structure of reality at the smallest scales. Newton watches these simulations, trying to understand how this quantum foam might affect the behavior of particles and the structure of the universe. He sees simulations of how quantum mechanics might affect the large-scale structure of the universe. Quantum fluctuations in the early universe might have created the seeds of galaxies and stars. The quantum computer shows how tiny quantum fluctuations, amplified by cosmic inflation, could have grown into the cosmic structures we see today. Newton watches as quantum fluctuations expand with the universe, growing into galaxies, stars, and planets. This connection between the quantum world and the cosmic scale fascinates him, showing how quantum mechanics might have shaped the entire universe. He does not yet have all the pieces. He does not know how to unify quantum mechanics and gravity, but he can see that they are connected, that a complete understanding of the universe will require understanding both. Today, researchers are using quantum computers to explore theories of quantum gravity. They simulate simplified models of how quantum mechanics and gravity might interact, testing different approaches to unification. These simulations help physicists understand which theories might be correct, and which need to be modified or abandoned. Quantum computers are providing new tools for exploring the deepest questions in physics, questions that have puzzled scientists for decades. Some researchers are exploring whether quantum computers themselves might provide insights into quantum gravity. The way qubits interact, the way quantum information flows through quantum circuits, might reveal something about how quantum mechanics and gravity are connected. This is still speculative, but it shows how quantum computing is opening new avenues for research, not just solving existing problems, but revealing new questions to explore. And this realization, this understanding of the strange nature of space and time, would shape how he thought about the universe for the rest of his life. The quantum computer has shown him glimpses of a universe far stranger than he imagined. A universe where space and time are relative, where particles can be in multiple places at once, where the smallest scales and largest scales are connected. A universe where reality itself might be fundamentally quantum, where observation creates reality, where the act of measuring changes what is measured. These are profound insights. Insights that would take centuries for scientists to discover and understand. But Newton has seen them. In the simulations, in the patterns, in the behavior of the quantum computer itself. He sits back, overwhelmed by what he has witnessed. The quantum computer has shown him possibilities he never imagined. It has revealed connections between phenomena he thought were separate. It has opened doors to understanding that he did not know existed. But it has also shown him how much he does not know, how many mysteries remain unsolved, how much there is still to discover. The quantum computer is a tool, a powerful tool, but it is not magic. It cannot think, it cannot understand. It can only process information according to rules it has been given. The insights, the understanding, the creativity, these still come from human minds. The quantum computer can show patterns, but it cannot explain why those patterns exist. It can simulate possibilities, but it cannot choose which possibilities are meaningful. It can calculate, but it cannot wonder. Newton realizes that the quantum computer, for all its power, is still just a tool. It extends human capabilities, but it does not replace human thought. The slow process of understanding, of building intuition, of asking questions, these are still essential. The quantum computer can accelerate discovery, but it cannot replace the wonder and curiosity that drive science forward. He also realizes that having powerful tools is not enough. The quantum computer can show him simulations, but he must still understand what those simulations mean. He must still interpret the results, connect them to what he knows, build new understanding from what he sees. The quantum computer provides answers, but he must still ask the right questions. It provides data, but he must still find the patterns. It provides possibilities, but he must still choose which to explore. This is a humbling realization. Even with the most powerful computing tool imaginable, understanding still requires human thought, discovery still requires curiosity, science still requires patience. The quantum computer is a remarkable tool, but it is not a substitute for the human mind. As Newton contemplates what he has learned, he realizes that science is not just about finding answers, it is about understanding why those answers are true. It is about seeing the deeper patterns, the connections between different phenomena, the underlying principles that govern reality. The quantum computer can help with this, but it cannot do it alone. It requires human insight, human creativity, human wonder. He also realizes that tools shape how we think. The quantum computer shows him the world in a new way, revealing quantum properties that were invisible before. That this new perspective also changes how he thinks about problems, how he approaches questions, how he understands reality. Tools do not just extend our capabilities, they transform our understanding. The quantum computer is not just a faster calculator, it is a new way of seeing the world. This transformation is both exciting and challenging. The quantum computer opens new possibilities, but it also requires new ways of thinking. Newton must learn to think in terms of probabilities rather than certainties, superpositions rather than definite states, entanglement rather than independent objects. This is a fundamental shift, one that would take scientists centuries to fully embrace. But Newton is glimpsing it now, centuries early, through the quantum computer's simulations. The quantum computer has shown him that reality is far stranger than he imagined, but it has also shown him that understanding this strange reality is possible. That with the right tools, the right questions, and the right patience, we can explore even the most mysterious aspects of nature. The quantum computer is one such tool, a powerful extension of human curiosity and creativity. How would quantum computing have changed science? How would it have changed history? With quantum computing, Newton could have made discoveries much faster. He could have tested ideas instantly. He could have explored possibilities that would have taken years with pen and paper. He might have discovered quantum mechanics centuries early. He might have understood the wave-particle nature of light. He might have seen the quantum nature of matter. He might have glimpsed the strange behaviors of quantum particles. This would have accelerated science dramatically. Other scientists would have built on Newton's discoveries. They would have explored quantum mechanics. They would have developed quantum technologies. Technology might have advanced much faster. Quantum computers might have been built earlier. Quantum sensors might have been developed. Quantum communication might have been possible. Society might have changed. New technologies would have emerged. New industries would have formed. The world might look very different, but there is a danger here too. Understanding quantum mechanics requires more than just computing power. It requires careful thought. It requires experiments. It requires building intuition slowly. If Newton had discovered quantum mechanics too quickly, he might not have understood it deeply. He might have seen the patterns but missed the meaning. He might have had the answers but not the questions. Science is not just about finding answers. It is about asking the right questions. It is about understanding why things work, not just that they work. The slow process of discovery has value. It allows scientists to build intuition. It allows them to understand deeply. It allows them to see connections they might miss if everything happened too fast. Quantum computing is a powerful tool. But it is still just a tool. It can calculate, it can simulate, it can explore possibilities. But it cannot think. It cannot understand. It cannot create new ideas. That requires human minds. It requires curiosity. It requires patience. It requires the slow, careful work of understanding. So perhaps it is good that Newton did not have quantum computing. Perhaps the slow process of discovery was necessary. Perhaps understanding had to be built gradually, one discovery at a time. But we can still imagine, we can still wonder, what if? What might have been? What could have happened? And in imagining we learn something important. We learn that tools are powerful, but understanding is more powerful. That computing can accelerate discovery, but it cannot replace thought. That the human mind, with all its limitations, is still the most remarkable tool of all. Quantum computing is powerful. It can solve problems that regular computers cannot. It can simulate complex systems. It can explore many possibilities at once. But it has limits. Quantum computing cannot think, it cannot understand, it cannot create new ideas. It can only process information according to rules it has been given. It cannot replace human intuition. It cannot replace careful observation. It cannot replace the slow process of understanding. Newton's greatest discoveries came not from powerful tools, but from his ability to see patterns, to ask the right questions, to think deeply about what he observed. His theory of gravity came from seeing connections others missed. His calculus came from needing new mathematics to describe motion. His understanding of light came from careful experiments and observation. These discoveries required more than calculation. They required insight. They required creativity. They required the human ability to see beyond what is obvious. Quantum computing could have helped Newton test his ideas. It could have shown him patterns. It could have accelerated his calculations. But it could not have given him the insights that made his discoveries possible. Understanding is not just about having answers. It is about knowing why those answers are true. It is about seeing the deeper patterns. It is about building intuition. This takes time. It takes careful thought. It takes the slow process of exploration and discovery. Quantum computing is a tool, a powerful tool, but it is still just a tool. It cannot replace the human mind. It cannot replace curiosity. It cannot replace the wonder that drives science. Newton would have realized this. Even with quantum computing, he would have needed to think carefully. He would have needed to understand what the simulations showed. He would have needed to build intuition slowly. The value of quantum computing is not that it replaces human thought, but that it extends it. It lets us explore possibilities we could not explore otherwise. It lets us test ideas we could not test otherwise. It lets us see patterns we could not see otherwise. But the understanding, the insight, the creativity, these still come from human minds. These still require the slow, careful work of thinking. So perhaps the greatest lesson is not about what quantum computing can do, but about what it cannot do, about the limits of tools, about the value of human thought. And perhaps this is the most important thing Newton would have learned, that tools are powerful, but understanding is more powerful. That computing can accelerate discovery, but it cannot replace the wonder and curiosity that drive science forward. Newton's discoveries shaped science for centuries. His laws of motion described how objects move. His theory of gravity explained planetary orbits. His calculus provided new mathematical tools. His work on light revealed the nature of color. But Newton's physics was classical physics. It described the world at everyday scales and speeds. It worked perfectly for the problems he could observe. It took centuries for scientists to discover that classical physics is part of a larger picture. That at very small scales, quantum mechanics applies. That at very high speeds, relativity applies. That these different sets of rules are all true, describing different aspects of reality. Today, scientists are still working to unify these different theories. To understand how quantum mechanics and gravity are connected, to find a theory that describes everything. Quantum computing is helping with this. It can simulate quantum systems. It can explore how quantum mechanics and gravity might be unified. It can test ideas that are difficult to test in the laboratory. Researchers are using quantum computers to simulate black holes, those mysterious objects where gravity becomes so strong that even light cannot escape. They simulate how quantum particles behave near black holes, testing theories about how quantum mechanics and gravity interact. These simulations help physicists understand what happens at the edge of our understanding, where space and time break down. In 2022, researchers used a quantum computer to simulate a simplified model of a black hole. They showed how information might be preserved as matter falls into a black hole, testing theories about black hole information paradox. This paradox asks what happens to information when it enters a black hole, a question that has puzzled physicists for decades. Quantum computers could help simulate these extreme conditions, testing theories that are impossible to test in laboratories. Scientists are also using quantum computers to simulate the early universe. They model how quantum fluctuations in the first moments after the Big Bang might have created the seeds of galaxies. They simulate how matter and energy behaved when the universe was incredibly dense and hot. These simulations help cosmologists understand how the universe evolved from a tiny hot point to the vast cosmos we see today. Researchers are using quantum computers to simulate cosmic inflation, the rapid expansion of the universe in its first moments. They model how quantum fluctuations during inflation might have created the density variations that later grew into galaxies and stars. These simulations help cosmologists understand the origin of cosmic structure, one of the biggest mysteries in physics. Quantum computers can handle the quantum nature of these early fluctuations, something classical computers struggle with. Climate scientists are exploring quantum computing to improve climate models. Current climate models are limited by computational power, forcing scientists to simplify complex processes. Quantum computers could simulate these processes more accurately, including quantum effects in atmospheric chemistry and cloud formation. Better climate models could improve predictions about global warming, helping society prepare for future changes. Some researchers are developing quantum algorithms specifically for climate simulation, though this application is still in early stages. Machine learning researchers are exploring quantum computing for artificial intelligence. They are developing quantum machine learning algorithms that could process information in new ways. Some researchers believe quantum computers could help train AI systems faster, or discover patterns that classical computers miss. Companies like Google and IBM are investing heavily in quantum machine learning, exploring whether quantum computers could give AI new capabilities. In 2022, researchers demonstrated that quantum computers could help train certain types of neural networks more efficiently. They showed that quantum algorithms could find patterns in data that classical algorithms missed. This could be especially useful for problems involving quantum data, like simulating quantum systems or analyzing quantum sensors. However, it is not yet clear whether quantum computers will provide advantages for most classical machine learning tasks. Some researchers are exploring quantum neural networks that use quantum mechanics to process information. These networks could potentially learn faster or discover different patterns than classical neural networks. However, building and training quantum neural networks is extremely difficult, and it is not yet clear whether they will be practical. Researchers are still exploring the fundamental limits and possibilities of quantum machine learning. Quantum computers are also being used to improve classical machine learning algorithms. Researchers use quantum computers to generate better training data or to optimize hyperparameters more efficiently. Some researchers believe that even small quantum computers could help improve classical AI systems, acting as specialized coprocessors for certain tasks. This hybrid approach might be more practical than fully quantum AI systems, at least in the near term. But quantum computing itself depends on quantum mechanics. It uses the strange behaviors of quantum particles to process information. It is both a tool for understanding quantum mechanics and a product of that understanding. The field faces real challenges. Quantum computers are still small, with error rates that limit their usefulness. Most quantum algorithms require thousands or millions of qubits to solve real-world problems, but current machines have only hundreds. Error correction will require even more qubits, perhaps millions, to create a single, reliable logical qubit. Scientists are working on improving qubit quality, reducing errors, and developing better error correction methods. They are exploring new materials, new designs, new approaches to building quantum computers. In 2023, researchers at Google announced a major breakthrough in quantum error correction. They demonstrated that their quantum error correction system could actually reduce errors as they added more qubits, a key requirement for building practical quantum computers. This was a significant milestone, showing that error correction could work in practice, not just in theory. However, they still need to improve the system dramatically before it can be used for real applications. Different companies are taking different approaches. IBM is building larger and larger quantum processors, working toward machines with thousands of qubits. Google is focusing on improving qubit quality and error correction. Companies like IonQ are using trapped ions, which are more stable but slower. PsiQuantum is building photonic quantum computers that could work at room temperature. Each approach has trade-offs, and it is not yet clear which will succeed. IBM has created a roadmap for quantum computing, planning to build processors with over 1,000 qubits by 2023, and eventually machines with millions of qubits. They are developing new error correction methods and improving qubit connectivity. Their goal is to build a quantum computer that can solve real-world problems, not just demonstrate quantum advantage. They have made their quantum computers available through the cloud, allowing researchers worldwide to experiment with them. Google is taking a different approach, focusing on improving qubit quality rather than just quantity. They are developing better materials and designs to reduce errors. Their goal is to build quantum computers with low enough error rates that error correction becomes practical. They have demonstrated that their error correction system can actually reduce errors, a crucial step toward practical quantum computing. IonQ uses trapped ions, atoms held in place by electric fields, and manipulated with lasers. Their qubits are more stable than superconducting qubits, with longer coherence times. However, they are slower to operate, making them less suitable for some applications. IonQ has built quantum computers with over 100 qubits and is working on scaling up further. PsiQuantum is building photonic quantum computers, using particles of light to carry quantum information. Their approach could work at room temperature, eliminating the need for expensive cooling systems. However, controlling photons is extremely difficult, and it is not yet clear whether photonic quantum computers can be scaled up. PsiQuantum is working on building a 1,000,000-qubit photonic quantum computer, though this goal is ambitious, and the timeline uncertain. Rigetti Computing is developing hybrid quantum classical systems, combining quantum processors with classical computers. They believe this approach will be more practical for near-term applications, using quantum computers for specific tasks, while relying on classical computers for the rest. They have built quantum processors with dozens of qubits, and are developing better integration with classical systems. Rigetti has formed partnerships with financial institutions and other companies to develop practical applications. They have created Forest, a quantum computing software platform that makes it easier to program quantum computers. D-Wave Systems was one of the first companies to commercialize quantum computing, though their approach is different from most others. They build quantum annealers, specialized quantum computers, designed for optimization problems. These machines are not universal quantum computers, but they can solve certain optimization problems efficiently. D-Wave has sold quantum annealers to companies like Volkswagen, Google, and NASA. The company has built machines with thousands of qubits, though they are designed for specific types of problems rather than general-purpose computing. Microsoft has invested heavily in quantum computing research, though they are taking a different approach. They are developing topological qubits that are protected from errors by their geometric properties. This approach could make quantum computers more stable and reliable, though it is extremely difficult to build. Microsoft has partnered with academic researchers and is building quantum computing infrastructure. They have created QHash, a programming language specifically designed for quantum computing, and have made quantum computing tools available through their Azure cloud platform. Amazon has launched Amazon Bracket, a quantum computing service that provides access to quantum computers from multiple companies. Users can run experiments on quantum computers from D-Wave, IonQ, and Rigetti through Amazon's cloud platform. This makes it easier for companies and researchers to experiment with quantum computing without building their own infrastructure. Amazon is also investing in quantum computing research, exploring applications in optimization and machine learning. Intel is developing quantum computers using silicon-based qubits, similar to the transistors used in classical computers. This approach could leverage Intel's expertise in semiconductor manufacturing, potentially making quantum computers easier to build and scale. The company has built small quantum processors, and is working on improving qubit quality. Intel sees quantum computing as a natural extension of their computing technology, though they acknowledge that practical quantum computers are still years away. Honeywell has built quantum computers using trapped ions, similar to IonQ's approach. The company has decades of experience in precision control systems, which is crucial for manipulating trapped ions. Honeywell has built quantum computers with high-quality qubits and has made them available through cloud services. The company has formed partnerships with financial institutions and other companies to explore quantum computing applications. Quantinuum, formed from the merger of Honeywell's quantum computing division and Cambridge Quantum Computing, is focusing on quantum software and applications. They are developing quantum algorithms for chemistry, finance, and optimization problems. The company has built quantum computers and is creating software tools to make quantum computing more accessible. They are working with pharmaceutical companies, financial institutions, and other organizations to develop practical applications. Other companies are exploring even more exotic approaches. Some are developing quantum computers based on neutral atoms, atoms that are not charged. Others are exploring topological qubits, qubits that are protected from errors by their geometric properties. Each approach has advantages and challenges, and the field is still exploring which will ultimately succeed. Governments around the world are investing billions in quantum computing research. China has built quantum computers and claims to have achieved quantum advantage in certain applications. The United States has launched a national quantum initiative, coordinating research across government agencies, universities, and companies. The European Union has a quantum flagship program, funding quantum research across Europe. These investments show how important quantum computing is considered to be for the future. China has made quantum computing a national priority, investing billions of dollars in research. They have built quantum computers and demonstrated quantum advantage in several applications. They have also built the world's largest quantum communication network, connecting cities over 2,000 kilometers apart. Chinese researchers have made significant advances in quantum error correction and quantum algorithms. The country sees quantum computing as crucial for economic and military competitiveness. The United States National Quantum Initiative was launched in 2018, coordinating quantum research across multiple agencies. The National Science Foundation funds basic research. The Department of Energy supports research at national laboratories. The National Institute of Standards and Technology develops quantum standards and measurements. The initiative has allocated billions of dollars for quantum research, recognizing it as a critical technology for national security and economic competitiveness. The European Union's Quantum Flagship Program is one of the largest quantum research initiatives in the world, with a budget of over €1 billion. It funds research across Europe, bringing together universities, companies, and research institutions. The program focuses on quantum computing, quantum communication, quantum sensing, and quantum simulation. It aims to make Europe a leader in quantum technology. Other countries are also investing heavily. Canada has become a hub for quantum computing companies, with D-Wave Systems and other companies based there. Australia has strong quantum research programs, particularly in quantum error correction. Japan has launched quantum research initiatives, focusing on both quantum computing and quantum communication. India has announced plans to invest billions in quantum research, recognizing it as crucial for technological development. These investments reflect a global race to develop quantum computing. Countries see it as crucial for economic competitiveness, national security, and scientific advancement. The country or company that develops practical quantum computers first could gain significant advantages in cryptography, drug discovery, materials, science, and other fields. This has created intense competition and collaboration in the field. The timeline for practical quantum computers is uncertain. Some experts believe we might see useful quantum computers within a decade. Others think it could take much longer. The challenges are significant, but progress continues. Each year brings new breakthroughs, new records, new possibilities. The field is advancing rapidly, driven by the promise of solving problems that seem impossible today. Some researchers are optimistic about near-term quantum applications. They believe that even current quantum computers, with their limitations, could be useful for certain problems. Quantum simulation, for example, might be practical on near-term quantum computers, even with high error rates. Some optimization problems might benefit from quantum algorithms running on noisy quantum computers. These near-term applications could provide value while researchers work on building better quantum computers. Other researchers are more cautious, believing that most practical applications will require fault-tolerant quantum computers, with millions of qubits and extremely low error rates. They point out that current quantum computers are still too small and too noisy for most applications. Error correction will require significant overhead, potentially needing thousands of physical qubits for each logical qubit. Building fault-tolerant quantum computers will be extremely difficult and expensive. Most experts agree that quantum computing will eventually be transformative, but disagree about when this will happen. Some believe we will see practical quantum computers within 10 to 20 years. Others think it could take 50 years or more. The timeline depends on many factors: advances in qubit quality, improvements in error correction, development of better algorithms, and continued investment in research. Progress could accelerate if there are major breakthroughs, or slow down if fundamental obstacles prove difficult to overcome. What is clear is that quantum computing research is advancing rapidly. Each year brings new records: more qubits, lower error rates, longer coherence times, better algorithms. Companies are investing billions. Governments are funding research. Universities are training quantum scientists. The field is growing and evolving. Whether practical quantum computers arrive in a decade or several decades, they will likely transform science, technology, and society in profound ways. The quantum computing workforce is growing rapidly. Universities worldwide are offering quantum computing courses and degrees. Thousands of students are learning quantum mechanics, quantum algorithms, and quantum programming. Companies are hiring quantum scientists, offering competitive salaries to attract talent. This growing workforce will be crucial for developing quantum computing applications and building practical quantum computers. Quantum computing education is becoming more accessible. Online courses teach quantum computing to anyone with an internet connection. Companies like IBM and Google provide free quantum computing resources and tutorials. Universities are creating quantum computing programs, training the next generation of quantum scientists. This education infrastructure will help ensure that quantum computing advances continue, even as the field becomes more complex. International collaboration is crucial for quantum computing progress. Researchers worldwide share their findings, collaborate on projects, and build on each other's work. Major quantum computing conferences bring together scientists from different countries and companies. This collaboration accelerates progress, as researchers can learn from each other and avoid duplicating work. However, there is also competition, as countries and companies race to develop quantum computing first. The quantum computing ecosystem is maturing. Beyond hardware and software, companies are developing quantum computing services, consulting, and support. Quantum computing cloud platforms, make it easier for companies to experiment with quantum computers. Quantum computing startups are creating specialized tools and services. This ecosystem will be crucial for making quantum computing accessible and practical for a wide range of applications. Quantum software companies are developing tools to make quantum computing easier to use. They are creating programming languages, development environments, and debugging tools specifically for quantum computing. These tools abstract away some of the complexity of quantum computing, making it more accessible to developers who are not quantum physics experts. As quantum computers become more powerful, these software tools will become increasingly important for developing practical applications. Quantum algorithm libraries are being developed to provide ready-made solutions for common problems. Instead of writing quantum algorithms from scratch, developers can use pre-built algorithms for optimization, machine learning, chemistry simulation, and other applications. These libraries will accelerate the development of quantum applications, allowing companies to focus on their specific use cases rather than low-level quantum programming. Quantum computing consulting firms are helping companies explore quantum computing applications. These firms help identify use cases, develop quantum algorithms, and integrate quantum computing into existing workflows. They provide expertise that many companies lack, making it easier for organizations to experiment with quantum computing. As quantum computing matures, consulting services will help companies adopt the technology more quickly. Quantum computing standards are being developed to ensure interoperability and compatibility. Standards organizations are working on protocols for quantum communication, quantum programming languages, and quantum hardware interfaces. These standards will be crucial as quantum computing scales, ensuring that different quantum computers and software can work together. Standards will also help accelerate adoption by providing clear guidelines for developers and companies. The Quantum Internet Alliance is working to develop standards for quantum communication networks. They are creating protocols for quantum key distribution, quantum teleportation, and other quantum communication methods. These standards will be essential for building a global quantum internet, ensuring that quantum communication systems from different vendors can work together. The alliance includes companies, universities, and research institutions from around the world. Quantum programming language standards are being developed to make quantum computing more accessible. While different companies have created their own quantum programming languages, standards organizations are working on common interfaces and protocols. This will allow developers to write quantum programs that can run on different quantum computers, similar to how classical programs can run on different computers. Standards will also help with education, as students can learn one standard language rather than multiple proprietary ones. Quantum hardware interface standards are being developed to ensure that quantum computers can work with classical computers and other systems. These standards define how quantum computers communicate with classical computers, how quantum algorithms are executed, and how results are returned. As quantum computing becomes more integrated into existing systems, these standards will be crucial for interoperability. Quantum benchmarking standards are being developed to measure and compare quantum computer performance. These standards define metrics for qubit quality, error rates, coherence times, and other important characteristics. They help researchers and companies understand which quantum computers are best for which applications, and track progress as quantum computers improve. Benchmarking standards also help identify areas where quantum computers need improvement. Some researchers are optimistic, believing that quantum computers will solve practical problems within the next decade. They point to rapid progress in error correction, qubit quality, and algorithms. They believe that continued investment and research will overcome current challenges. However, they acknowledge that many obstacles remain, and success is not guaranteed. Other researchers are more cautious, believing that practical quantum computers are still decades away. They point to the enormous challenges of scaling up quantum computers, reducing errors, and developing useful algorithms. They note that many promised applications remain theoretical, and it is not yet clear whether quantum computers will provide advantages for most real-world problems. They believe that progress will be slower and more difficult than optimists predict. Most researchers agree that quantum computers will eventually be useful, but disagree about when and for what applications. Some applications, like quantum simulation, might be practical sooner. Others, like breaking encryption, might require much larger quantum computers. The field is still exploring which applications will be most valuable, and when they will become practical. What is clear is that quantum computing is advancing rapidly. Each year brings new records, new breakthroughs, new possibilities. Companies are investing billions. Governments are funding research. Universities are training the next generation of quantum scientists. The field is growing, evolving, and advancing. Whether practical quantum computers arrive in a decade or several decades, they will likely transform science, technology, and society in ways we can only begin to imagine. Quantum sensing is another area where quantum technology is already showing practical applications. Quantum sensors use quantum properties to measure physical quantities with incredible precision. They can detect tiny magnetic fields, measure time with extreme accuracy, and sense gravitational waves. These sensors are already being used in navigation, medical imaging, and scientific research. They do not require full quantum computers, just the ability to control quantum states precisely. Quantum sensors could revolutionize many fields. They could detect underground resources, map the Earth's interior, and monitor climate change. They could improve medical imaging, detecting diseases earlier and more accurately. They could enable new forms of navigation that do not rely on GPS. Quantum sensing is already practical, showing that quantum technology can provide real benefits even before full quantum computers are available. Quantum magnetometers can detect tiny magnetic fields with incredible precision. They are already being used to map the Earth's magnetic field, helping geologists find mineral deposits and oil reserves. They can detect submarines underwater by sensing their magnetic signatures. They can monitor brain activity by detecting the tiny magnetic fields produced by neural activity. These sensors are more sensitive than classical magnetometers, enabling new applications in science, medicine, and security. Quantum clocks are the most accurate timekeeping devices ever created. They can measure time with precision better than 1 second in billions of years. These clocks use the quantum properties of atoms to keep time, measuring the vibrations of electrons as they jump between energy levels. Quantum clocks are already being used to improve GPS accuracy, test fundamental physics theories, and synchronize global communication networks. They could enable new forms of navigation that do not require satellites, using quantum clocks to measure position from Earth's gravitational field. Quantum gravimeters measure gravitational fields with extreme precision. They can detect tiny variations in gravity caused by underground structures, helping archaeologists find buried ruins, and geologists map the Earth's interior. They can monitor changes in groundwater levels, detect underground tunnels, and study the movement of tectonic plates. These sensors are already being used in scientific research, and could have applications in resource exploration and national security. Quantum imaging uses quantum properties to create images with resolution beyond classical limits. Quantum sensors can detect single photons, enabling imaging in extremely low light conditions. They can create images using quantum entanglement, potentially achieving resolution beyond what classical physics allows. These techniques could improve medical imaging, allowing doctors to see inside the body with greater detail and less radiation. They could enable new forms of microscopy, revealing structures too small for classical microscopes to see. Quantum radar is being developed for military and civilian applications. Unlike classical radar, which sends out radio waves and detects their reflections, quantum radar uses entangled photons. This could make it harder to detect and jam, potentially providing advantages in military applications. Quantum radar could also be more sensitive, detecting smaller objects at greater distances. However, quantum radar is still in early stages of development, and it is not yet clear whether it will provide practical advantages over classical radar. Quantum LiDAR uses quantum properties to measure distances with extreme precision. LiDAR systems send out laser pulses and measure how long they take to bounce back, creating detailed three-dimensional maps. Quantum LiDAR could be more sensitive and accurate than classical LiDAR, enabling better autonomous vehicle navigation, archaeological surveys, and environmental monitoring. Some companies are already developing quantum LiDAR systems, though they are still experimental. Quantum communication systems are being built to create secure communication networks. These systems use quantum key distribution to create encryption keys that cannot be intercepted without detection. China has built the world's largest quantum communication network, connecting cities over 2,000 kilometers apart. Other countries are also building quantum communication networks, recognizing their potential for secure communication. Quantum communication could protect sensitive information from future quantum computers that might break classical encryption. Quantum Internet is a long-term goal that would connect quantum computers worldwide, enabling distributed quantum computing and secure quantum communication. Researchers are developing the technologies needed for a quantum internet, including quantum repeaters that can extend the range of quantum communication. A quantum internet could enable new applications, like distributed quantum sensing, quantum cloud computing, and secure quantum communication on a global scale. However, building a quantum internet will require significant advances in quantum technology and infrastructure. This is a beautiful circle. Newton's classical physics led, centuries later, to quantum mechanics. Quantum mechanics led to quantum computing. And quantum computing is helping us understand quantum mechanics better, and perhaps helping us unify it with gravity. Newton's work was not complete, but it was essential. It provided the foundation, it showed the way forward, it opened the door to deeper understanding. Today, we stand on Newton's shoulders. We see farther because he showed us how to look. We understand more because he showed us how to think. Quantum computing is part of this journey. It is a tool that extends our ability to explore and understand. But it is not the end of the journey. There is always more to discover. Always new mysteries to explore. Always new questions to ask. And perhaps this is Newton's greatest legacy, not the specific discoveries he made, but the way he approached science. The curiosity. The careful observation, the patient thinking, the willingness to question assumptions and explore new ideas. These qualities are still essential today. Quantum computing can help us explore, but it cannot replace the human qualities that drive science forward: the wonder, the curiosity, the patience, the creativity. So as we imagine Newton with quantum computing, we remember that the most important tool is not the computer, but the human mind. Not the calculation, but the understanding. Not the answer, but the question. And in this we honor Newton's legacy. We continue the journey he began. We build on what he discovered, and we keep asking, what if? What might be? What can we understand? As our journey comes to an end, you can let your mind drift gently. You have traveled through time, from Newton's 17th century England to the quantum computers of today. You have explored what quantum computing is, how it works, and how it might have transformed Newton's discoveries. You have seen how quantum computing uses the strange behaviors of quantum particles to process information, how it can solve problems that regular computers cannot, how it can simulate complex systems and explore many possibilities at once. You have imagined Newton encountering this powerful technology, how it might have accelerated his work on gravity, light, and motion, how it might have revealed the quantum nature of reality centuries early. You have also seen the limits of tools, how computing power cannot replace understanding, how the slow process of discovery has value, how human curiosity and creativity are still the most important tools of all. Science is a journey. It builds on what came before. Each discovery opens new questions. Each answer reveals new mysteries. Newton's work led to quantum mechanics. Quantum mechanics led to quantum computing. And quantum computing is helping us understand quantum mechanics better. This is how science progresses. Not in straight lines but in spirals. Coming back to old questions with new tools. Seeing familiar things in new ways. Building understanding layer by layer. You do not need to remember every detail of this journey. You can let the ideas settle gently in your mind. The understanding of quantum computing. The connection to Newton's discoveries. The wonder of how science builds on itself. If you drift off to sleep, that is perfectly fine. The story will keep going. Science will keep progressing. New discoveries will be made. New questions will be asked. And perhaps, as you rest, your mind will continue exploring, making connections, asking questions, wondering what might be possible. Thank you for joining me on this journey through time and science. If these gentle explorations help you rest or satisfy your curiosity, you are always welcome to return. The story of science continues. The journey of discovery never ends. And somewhere, in some quiet room, someone is asking a new question, exploring a new possibility, building on what came before. Sweet dreams, and keep wondering about the universe. Good night.